waste much of your time anymore and just give you a brief introduction. So today we will have a really special guest. His name is Professor Quentin Parker, and he will be joining us live from Hong Kong, where he currently resides, because Professor Parker has been working for the Australian Astronomical Observatory until 2015. And after 2015, he has moved on to teach at the University of Hong Kong, where he currently is and currently resides, and where he also directs Laboratory for Space Research. He will tell you something more about what Laboratory for Space Research does and what his research is focused on a little bit later. And I would like guys to give a little round warm of applause to Mr. Professor Parker. So say hello to Mr. Professor Parker.
Hello, everybody.
Hello, Professor
I hope you can hear me.
Thank you for joining us.
Well, it's evening for me, and it's different times all over the world for everybody else.
That's right. So thank you very much for joining us. It's a great pleasure and honor to have you on board, and you're a true expert in the field, and we just can't wait to hear what you guys have to say about space exploration and what you guys know about the dark matter. So without any further ado, would you perhaps like to tell us something more about yourself? Perhaps what is your educational background, and why did you choose astronomy and astrophysics for your research?
Okay, thank you very much for the question. It's a real pleasure too for me to be here, and a privilege to be able to reach out to so many people in, I think you said, more than 20 different countries around the world. So hello everybody. I hope I can give some interest to what I'm going to say. So my background is I was born in the UK, but I'm an Australian citizen. I consider myself Australian, but I was born in the UK and educated in Scotland at the University of St Andrews, which has a long and illustrious career in astronomy. In fact, the James Gregory, the Gregorian telescope was designed at St Andrews, and the university was founded in 1411. So it's the third oldest university in the United Kingdom, and I did an honours degree in astronomy and astrophysics there. Why astronomy and astrophysics? Well, I went to St Andrews because they had all the best telescopes currently in the UK. The big one moved from Greenwich into the Canary Islands some years ago. So the ones still based in the UK, the best ones were at University of St Andrews. And I always wanted to use the telescope, so I decided to the degree up there. From there, I worked at the Royal Observatory in Edinburgh for many years as a higher and then senior scientific officer. And then I went out to work at the United Kingdom Schmidt Telescope in Australia, and then moved to the Anglo-Australian Observatory, which then became the Australian Astronomical Observatory. So we kept the logo. We just changed the name when the UK pulled out of the 3.9 meter AAT where I worked. And then after a while, I built up something called the Macquarie Astronomy, Astrophysics and Astrophotonics Research Centre. And once I finished with that, I had an opportunity to come to the University of Hong Kong as the head of physics. So I did that, but while there, I became director of something called the Laboratory for Space Research. And you'll hear a little bit more about that later. So that's a kind of quick potted history of my background. And one of the things I'm most known for is planetary nebulae. I've discovered, I think, about almost 1,500 planetary nebulae.
Wow.
So that's my, one claim to fame. But anyway, and I've discovered a comet many years ago when I was at the Schmidt telescope. But anyway, I'll stop there. That's my introduction.
I just have to ask you now, did you name the comet after yourself when you discovered it?
Well, that is the tradition. So the comet is actually called Comet Parker-Hartley. My great friend Malcolm Hartley and I discovered that comet. I found it first in the film. He confirmed it for me, and it's called Comet Parker-Hartley. Short period comet of no great significance.
But a comet
apparently,
never
I've seen one person who thinks I'm like Sheldon from The Big Bang Theory. So thank you very much for that comment. From Igor Cañero. Muy bien, mon ami.
Lovely. Has the comet,
Okay.
where was it? Was it in
Ready
our
for
galaxy?
question two?
Oh, sorry. Let me move on to question two
Sorry,
then.
yes.
You have mentioned Laboratory for Space Research. Would you mind telling us, what do you guys do?
Oh, thank you for that. Yes, the laboratory set up in 2016 under the previous Dean of Science at Hong Kong, very famous professor, Professor Sun Kwok. He's also a great expert in planetary nebulae like myself. So he set this laboratory up, and it's basically an interdisciplinary laboratory. So we have people from 5 different departments and 2 different faculties at the University of Hong Kong. We've got engineers, we've got astrobiologists, we've got computational chemists, and we've got people that are doing remote sensing, astrophysicists, high energy physicists, and all of these come together into this laboratory where we can sort of have synergies between areas that maybe don't talk to each other previously, but now you can kind of overlap, share ideas, interact, generate new ideas, come up with new initiatives and new plans. So if you look at our website, you can find out all about us and what we do. We have about 40 members currently, a mixture of faculty and postdocs and PhD students, master's students, interns, and associates. So that's the LSR.
That's quite a bunch of people. Is it an international crowd?
Yeah, it's not bad. Sorry, say again?
Is it an international crowd? Are those researchers from all around the world, just like our attendees?
Oh, they are. I mean, my deputy director, one of them is a guy called Joe Machowski. He's originally from the United States. My other deputy director is Su Meng. He's from near Beijing, from the mainland of China. I'm an Australian with British heritage. I've got a postdoc that's Iranian, another postdoc that's from Germany. I'm just employing another postdoc that's come from the UK, PhD students from Greece. And, well, you know, we're very cosmopolitan.
Lovely. It's like a UN.
Which is fantastic. Really fantastic.
Excellent. That's great to hear. Now, I have mentioned earlier that the topic of this specific webinar would be in search of dark matter. And I believe many of our attendees here today would like to know something more about it. I have heard that according to researchers, dark matter constitutes about 95% of the universe. And I was wondering if you could tell us perhaps what exactly dark matter is.
Well, we'd all like to learn a little bit more about dark matter, actually, because we don't really know very much about it. And actually, I'll just correct you there, 27% of the universe we think is dark matter. 5% is normal matter, like us, what we're made of, protons and neutrons and electrons and all those kind of things. That's so-called baryonic matter. That makes just under 5% of the universe. 27% is dark matter, and we don't know what it is. And the other part of the universe is something called dark energy. 68% of the universe is supposedly made of dark energy. So together you add it up and it's about 100%. And so dark matter, it's a very interesting topic. It's been studied for many decades now, and we kind of infer that it has to be there by the effect it has, by the gravity that it affects other things around it. So if you look at a rotation curve of a galaxy, for example, and you consider it like a Keplerian disk, and you look at the velocity of stars as they orbit the center of the galaxy, and then you look at the amount of light you can see in stars, so that's where the gas is, that's where the matter is, that's where the baryonic matter is, and you look at the velocities of the stars out there, you find out, well, what's holding up that velocity curve? It should be declining, but it's still horizontal at the same velocities. And so the only way to explain that is if there's more matter there than you can see. So that's one of the very first big observational evidence that there must be more matter in a galaxy than is obvious from all the light that you can see. And of course, all the light, all the photons comes from objects like stars and ionized gas clouds, H2 regions, planetary nebulae, supernova explosions, etc. So, but when you add all that up, it doesn't come to the amount of matter that should be there according to the way that gravity works to keep the rotation curve of a galaxy flat. The other thing is you look at galaxies themselves moving around in clusters, and you find that these galaxies are moving around far too fast for the cluster to be actually still exist today. If they were moving that fast for the time the galaxy has existed, then the galaxy would have evaporated away. All the galaxies would have flown off and disappeared by now. But because the cluster still exists, there must be more gravity holding the galaxies together in the cluster. And again, the only way to explain that is to invoke some kind of hidden matter that we can't see. That's called dark matter. So that's the mystery, and there's been lots of people trying to unravel that mystery for a very long time indeed. And all kinds of theories and ideas have been postulated to help us explain what dark matter could be. And so some things like MACHOs, massive compact halo objects, weird and exotic fundamental particles that we haven't yet discovered. So there's all kinds of ideas there. But to be honest, today, in the 21st century, on the 6th of June 2020, we still don't know what it is. I'm sorry, we don't.
That means we have something to look forward to. If we don't know what it is yet, one day we will learn, and that just gives us something. I'm sure we will.
Or we'll completely change physics. You know, that's the other option. We completely change physics. Because, as I said, I talked about dark matter, but there's this other thing, which I know is another question you have for me, called dark energy.
That's right.
Now, if you think dark matter is weird, wait till you hear about dark energy. Dark energy, I mean, we postulated that there needs to be something because we've discovered that the universe isn't just expanding. I mean, you've all heard of the Big Bang. You all know that the universe is expanding. And when I was growing up and becoming a junior astrophysicist, there was all sorts of debates about the universe. Would it expand forever? Would it collapse in on itself again, you know, and in a big crunch? But then through looking at a kind of supernova called Type 1a supernova, and we believe that these are called standard candles. That is to say, it doesn't matter where a Type 1a supernova goes off anywhere in a galaxy in the universe, it will always have a maximum brightness, like an absolute magnitude at maximum light, which you can use as a fiducial to calibrate your universe. And when you do that, and if you believe that Type 1a supernova today are the same as what they were much earlier in the history of the universe, then in order to explain what you see, the universe must be accelerating. Not only is it expanding, it's an expanding at an accelerated rate. And the only way to explain that is to invoke something called dark energy, which, when you do all the calculations, needs to account for about 68% of the universe. And we have no idea what that dark energy is, except that it's probably a property of space-time itself. So, you know, I don't find it very satisfactory as a scientist that we have no idea what's causing the universe to expand at an accelerated rate. But hey, I'm thinking, well, we're assuming here that Type 1a supernova remain the same throughout cosmic time. Well, what if they haven't? What if the fact that early supernova have a different metallicity because they come from an early kind of stars when they're less enriched with metals? So why can't that mean that the maximum light isn't the same? And if you could calibrate it out, maybe dark energy would go away. But, you know, there's a lot of postulation around this. But at the moment, everybody, well, the best guess is there must be dark energy. And certainly the evidence for dark matter is far, far stronger than the evidence for dark energy, which is based on, as I said, the accelerating expansion of the universe.
That sounds like a great, great mystery that somebody needs to solve one day. Because as humans, we're...
I wish I could do it. I'm just not clever enough. I'm sorry.
Oh, I don't believe that. Maybe you just need a little bit more time.
I
know. So you've mentioned that we have more proof of dark matter existing than we have of dark energy. What would happen to those clusters of galaxies that you've brought up earlier without the dark matter?
Well, they wouldn't exist because the speeds that we're measuring galaxies orbiting around cores of the galaxy clusters, because there's a, you know, at the center of rich clusters of galaxies, there's these so-called central dominant galaxies, they're very large, massive galaxies, usually with a supermassive black hole in the center, devoid of all gas, not forming stars anymore, bright orange in color. But, you know, they're the deep potential well of a galaxy cluster. But the galaxies themselves are moving at all kinds of velocities, and they're moving too fast, so that if only the matter that was there that was in the matter you see in stars, these clusters would already have evaporated. The escape velocity of these other galaxies would have moved them out from the potential well of the cluster, and the gravitational attraction wasn't strong enough, and these clusters were dissipated and dissolved. But because they haven't, and yet the motions are still so fast, there must be more matter there that we can't see holding these things together, and that's dark matter.
I see.
And also, you can tell it's there when you look at lensing. You've heard of, I don't know if you've heard of things called gravitational lensing. Famous one is, you know, when you can see some amazing images now on the internet of very deep images of clusters of galaxies, when all of a sudden it looks like there's arcs. There's all kinds of strange arcs, in blue usually. And these are background galaxies where the galaxy cluster is acting like a lens because gravity bends light. And so distant galaxies behind the cluster are being morphed into these arc shapes. And you see that, and it's called gravitational lensing. In fact, when you look at gravitational lensing and sort of a small-scale lensing, again, you can only explain the lensing you see not by the visible galaxies in the cluster, but by the dark matter that has to be present. So there's all kinds of strands of observational evidence for why dark matter must exist, from rotation curves of galaxies, from galaxy cluster kinematics to gravitational lensing.
Wow, that sounds...
I don't know if that's clear to people. Sort of clear to me in my mind at the moment, but, you know, it is 8:30 on a Saturday.
It is really early here as well. Now, you've mentioned the percentages of, you know, the matter that we know as us and all the atoms that things are made of, and you've mentioned also the percentage of dark matter and dark energy. The percentage of dark matter was something about 20-odd, am I correct?
27%, we think.
How do you measure the mass of it? How can we even know what are the percentages here? How do we detect it?
Well, well, you have an overall budget for a universe in terms of the energy, and you know, E equals mc squared. I mean, that is, in fact, when my son was born, the very first thing I said to him was E equals mc squared, and he said back to me, "Yes, Dad, I know." No, he didn't, but anyway, E equals mc squared, and so energy and matter are intimately connected through that equation from Einstein. And so we have an overall budget for the universe, and we look at all the baryonic matter. By that I mean stars. Stars in our universe that we can look at, measure the light from, estimate a mass of, etc. Because we have an initial mass function, we know the range of masses of stars. We can look at the way gravity works in individual galaxies, in clusters of galaxies, in large-scale structures of the universe. The very biggest things are rich clusters of galaxies. And we can work out from the way these work, from our understanding of gravity, how much mass is needed to account for the gravitational effects that you see. And that's just F equals G1, M1, M2, G over R squared, and you can work out from forces what the masses must be. So we can work out what mass there must be there in terms of dark matter. Now, and sort of dark energy is what we need to explain the energy budget for the accelerating universe. And so we think from the gravity and the more local scaling in our own galaxy and in other galaxies and clusters of galaxies, what the baryonic and dark matter budget is. And in the larger scale structures of the universe, and given that it's accelerating away, we know what the total budget must be, and the rest has to be accounted for in dark energy. So we have all kinds of cosmologies like, you know, lambda CDM, which is cold dark matter cosmologies, is a favored one. By cold dark matter, it means, you know, hot dark matter, warm dark matter, cold dark matter. It's to do with the energy of the particles of dark matter, or whatever the dark matter is. And so we have, you know, one theory is that all the dark matter is in primordial black holes. You know, these are black holes that are created very, very early in the history of the universe, and have masses of about 10 to the 18 kilograms. And if you're wondering, that doesn't sound like a lot, or it sounds like a lot, it is, but then it's only 10 to the minus 12 of the mass of our sun. So suddenly it doesn't sound like a lot. So it all depends on what you're comparing it with. So anyway, and that's one theory, that a lot of the dark matter could be in these primordial black holes. But then again, a lot of them would have irradiated away, if they're too small, through Hawking radiation, and would have already evaporated. So that sort of puts limits on the kind of mass that they must have to still account for dark matter today. Now, I have to say to the audience, I am not a theoretical cosmologist. I am an observational astrophysicist. And so I do most of my work through looking through telescopes, well, not with my own eye. Usually it's a detector that looks through collects the data, spectroscopy, narrowband images, analyzing, interpreting the data. And that's the kind of thing I do. I am too stupid to be a theoretician doing all those very complicated mathematical equations. I leave that to the geniuses like Steve Hawking and the rest of them. I just sort of collect data, analyze it, try to interpret it, try to write papers that make sense, and try to make sense of the universe, because it is a very complicated place.
Oh, indeed. Indeed. And from the way you talk about it, it only gets more complicated the more we know about it.
Yeah, yes. Very complicated.
You've mentioned black holes and dark matter interacting with each other. So do you think there's any kind of relation between the two? Could perhaps dark matter come
Well, as I'm saying, well, in fact, black holes, it's nothing darker than a black hole, as you probably know. And the energy density, the matter density is so high that the escape velocity is greater than the speed of light. So that's why it's a black hole. And we've actually recently, with using a whole Earth telescope, imaged the region very close to a black hole. Now, people made the mistake of thinking, oh, you've taken a photograph of a black hole. No. We've taken and created imagery of what's going on very close to the edge of the black hole, only in those wonderful images that you've seen and been very famous. But, you know, the fact of the matter is, I said, one candidate for what dark matter could be is vast numbers of very small primordial black holes. And these very small black holes could even be the seeds of the supermassive black holes that we now have in the center of almost all galaxies.
I see. You've mentioned that photo. Yes?
In fact, just quickly, in our, you know, you've probably heard of Planet X. Has everybody heard of Planet X? You think there's another planet out there somewhere? Been looking for it for decades. A big planet that seems to be needed to account for some of the minor gravitational orbital perturbations that we see in the solar system in amongst the major planets. And one of the latest ideas is that a black hole the size of a tennis ball would be enough to create the effect that we supposedly due to this Planet X, which no one's been able to find. And why can't they find it? Well, perhaps it's this tennis ball sized black hole. And so, you know, that's dark matter right there.
Wow, it's just a gift that keeps on giving, isn't it? We can explain many things using the dark matter. You have mentioned the photo. Well, what we suspected was the photo, but what you said is just an basically a simulation of the black hole. Do you think that one day technology will be advanced enough to capture dark matter in the way that it looks?
Who knows what the future will bring? I mean, you know, what today is commonplace, even 30 years ago, was science fiction. Who would have thought that we would have basically a Star Trek tricorder in everybody's hands, which in fact, even to work, you know, it's also a telephone, by the way, in case you were wondering. You can actually make calls with it as well as using all the millions of apps that are available. But in order for it to work, to do the GPS, it relies on Einstein's theories of relativity, because the time difference with those satellites moving around in the geostationary orbits, in order to keep the timing correct to the tiny fractions of a second, to the picosecond, to the femtosecond, you need to take account of relativity, even in that. So a slight digression there, I'm sorry to say. But anyway, what was your question again? I slightly...
Whether we will be able to one day perhaps take a photo of dark matter.
Hence the phone. Yes, I don't know. I don't really know, because at the moment, dark matter doesn't seem to interact with any normal matter. It's not giving out photons that we can detect across any part of the electromagnetic spectrum. So we can't measure it in terms of directly through photons, and we can't see it, which hence the name. So all we can see is the effect that it has on things that we can measure. So we can see the effect that the gravity of this dark matter has, because it has mass, the effect that the gravity has. And we can see that. There's a very famous two clusters of galaxies smashing into each other and passing through called the Bullet Cluster. That's probably one of the best maps of dark matter that we've currently got, because you look at the X-ray data, the hot gas, which is showing you where the energy is in baryons, etc. But then we look at the gravitational lensing, which I mentioned earlier, and that shows where the gravity from the dark matter is. And you can actually then see a kind of map of, well, the baryonic matter's here and the dark matter's here. And you can kind of see it. We've actually started being able to map dark matter through the other effects I've talked about. Even though we can't see it, we know it's there, and we can kind of map where it is. That's the stage we're at the moment.
Wow, excellent. Well, I hope that one day we will have answers to all of those questions. I see that our attendees are super interested in more information about dark matter. We will give them a chance to ask their questions a little bit later in the Q&A session. But I would like to move on to telescopes, because you've mentioned that that is pretty much your area of study, and you have created one telescope. Am I correct? It has something to do with lobster eye. It has a really exotic name.
Well, you see, I love seafood, you see, that's why. No, but seriously, the University of Hong Kong, in partnership with a great partner university of ours in the mainland of China called Nanjing University, we are the science leads on this Hong Kong Nanjing #1 satellite, which is kind of a lobster eye technology for imaging X-rays in the low energy band of X-rays. And this satellite, it's only basically a microsatellite. It's about 43 kilograms in size, and it's kind of yay big. You know, I guess it would be about 60 by 60 by 80 centimeters before the solar panels come out. So it's not a CubeSat. It's much bigger than a CubeSat, but it's a modest-sized satellite, and it's launching on July the 25th, all being well, from a rocket up in northern China. And it's the very first satellite science mission from any university in this part of the world, from Hong Kong, SAR. And we're very proud of it, and we're kind of doing the science lead. We'll be analyzing the data along with our collaborators at Nanjing University. And so, but the satellite itself has been built by a company called BISME. BISME stands for Beijing Institute for Science and Mechanical Electricity. Strange name for a company. But anyway, this company is very successful in the mainland for building large kinds of satellite, a lot of remote sensing satellite, but other things as well. It's moving into space research and space science. And so this is a big deal for them as well. So they've, with our input, they've sort of built the payload, which is a satellite, and as I said, it's launching in July. So we're very interested in the science that this satellite can do. We've helped to characterize, you know, the parameters of the instrument and what it needs to be able to do, so the specifications, and we've had input into the design, but basically we are the science lead for doing the science of this satellite. So there's nothing in Hong Kong apart from a model. We have a full-scale model in my laboratory, but the actual telescope satellite was manufactured in the mainland, and it's, I think, being mated with the telescope very shortly. It's finished, it's complete, I've seen it, it's ready to go, and we're very excited.
Will you be there for the launch, when they launch it? You mentioned it was
good question. My deputy director, Meng Su, he will be there right at the launch, and it won't be the first time he's launched there. But unfortunately, due to permissions up that part of China around the launch area, I might be able to get reasonably close by. I'm still working on that, but I won't be able to be, I don't think at this stage, at the launch myself, although I very much would like to be. But my deputy director, who's from the mainland of China, he will be there on my behalf, that's for sure.
Excellent. And you have mentioned your love for seafood, but I don't believe that. I'm sorry?
My deputy, he's called Dr. Meng Su. Yeah. Very good, very top guy.
Excellent. Now, you have mentioned your love for seafood, but I don't believe that was the only motivation for designing this telescope according to a lobster eye. So are there any other reasons? Does the shape of it bring any particular advantages for other shaped telescopes?
Yeah, I mean, this kind of idea of being able to focus and collimate X-rays using the kind of idea that like a lobster eye is created. If you look at any images online about, oh, what's a lobster eye? It's a bit like a compound eye of a fly. I think you can all remember that. But it's more, instead of round, they're kind of like rectangles. These components of the eye of a lobster, like rectangular components, which go in depth. And so we're using that kind of idea from nature as a way to actually, the way that you're able to focus X-rays. X-rays are high energy photons. If you had a normal glass mirror with an aluminium or gold coating on it, it would just go straight through. So what you do with X-rays, they come in at grazing incidence, so that when the angle of incidence is extremely low, then the X-rays can be reflected. And so that's what you have kind of with this compound lobster eye rectangular entrance aperture system in a grid, is all the X-ray photons are coming in, hitting the edges of these at very low angles, and then they get collimated and focused onto the X-ray detector at the back end of the telescope. So it's not, I mean, this idea has been around for quite some time. People have been working on it. NASA's worked on it before, but this is the first time I think that an X-ray science mission using this technology is being launched, certainly in China. And so again, it's very exciting. Now, the other advantage of this kind of telescope designed for X-rays, unlike the Herschel X-ray telescope and the Chandra X-ray telescope, massive telescopes in space with extremely long tubes of nested metal surfaces, so you can collimate the X-rays through grazing instance. We work here by having a big field of view. So the field of view of our satellite is 2 by 2 degrees on the sky, which is large, and it actually has very low weight. So, which is why we can fit it inside a 43-kilogram satellite. Mm-hmm. So the advantages are field of view and the weight budget, and also the way that the lobster eye technology works to focus X-ray. So it's a very promising technology, and it's been developed and honed and refined up in the mainland with BISME, our very strong partner company. And I'll tell you a bit more about them a bit later on when I get to talk about our top postgraduate masters in space science, because they're great partners of ours in that for scholarships. But anyway, so it's a combination of weight, cost, capacity, and field of view. All of these things coming together to create a fairly neat bundle that we believe is a very powerful, low-cost X-ray focusing, low-energy telescope using the eyes of a lobster. Well, not really the eyes of a lobster, of course, but
not the real lobster eyes.
Yeah, not real lobster eyes, no.
Good. We're happy to know that no lobsters have been harmed during your research and development of this telescope.
Yeah, no. I have eaten a few, though. Eaten a few of them, I'm sorry to say.
Oh, well.
Very tasty.
For science. For science.
Yes, for science. Purely scientific purposes, I assure you.
Great. Happy to hear that. I was wondering, it sounds like a crazy complex kind of technology. How long does it take to develop this kind of project? How long have you guys been working on it? And you've also mentioned low cost. If it's not a secret, could you perhaps tell me how much would this telescope cost?
Yes. Yes, I can. So this entire telescope has cost around 170 million yuan, or renminbi, so that's Chinese currency. So you can convert that into US dollars, and you'll see that that's actually quite a modest cost for such a satellite. The contributions from the universities of Nanjing U and Hong Kong U will be around 20-odd million renminbi only, because we're universities and we don't have the budgets to spend hundreds of millions of dollars on satellites. We're not rich like that. We're a university. I mean, some universities in America are very rich like that, of course, but most of the rest of the universities in the world are not. Hong Kong U is quite a well-off university in many respects, but it certainly cannot afford to spend 170 million renminbi on a satellite. But we have put in what we can for our intellectual input as the science leads on this, and we're trying to pay our share. But obviously, companies like BISME, who again, you know, China is trying to demonstrate some kind of move away into more commercial and also civilian space ventures, including big science missions. As you know, they've already put they've already gone to the backside of the moon recently with Chang'e 4 mission. They're going to Mars. They're building a space station. They're going back to the moon, and so is America and Europe. So you know, there's India's doing its thing, and the Europeans are doing their thing, and America and China are doing their thing, and so there's a lot of activity now in the 21st century in space. And I think it's great, especially if we can all cooperate together in a friendly fashion.
Exactly.
That would be even greater, my personal view.
Sometimes we can't really make peace here on Earth, but I hope at least in space we can be all friends and partners in crime.
Well, the planet desperately needs us to get along.
And at least maybe in space. We can start by that. Seems like we're struggling with doing it peacefully here on Earth so far.
Well, but I think what's happening with the world with this terrible, terrible virus that's affecting so many people's lives, it's also giving people, I think, a time to reflect a little on what's really important. And I think maybe at the end of it, after it's passed through, maybe we'll have a greener planet, you know, a more cooperative planet. That's what I hope personally, deep within.
Yeah, I hope that if we were to learn one lesson from this, maybe cooperation and helping each other out will be one of the most important ones. And speaking of cooperation, does Hong Kong or University of Hong Kong work with other perhaps space agencies or with other universities apart from, you've mentioned Nanjing, but any other universities perhaps, or any other agencies such as NASA? Do you guys cooperate with those?
Great question. Yeah, great question. We've signed, I think, about 19 memorandum of understanding over the last 2 years with all the top groups, certainly in the mainland, but also, with the Natural History Museum in London. Why with them? Well, they have one of the world's best meteorite collections, and also the world's best collection of meteorites from Mars, at least one of the top 2. And so if we're interested in resource extraction from asteroids in the future, having real material that we can study in labs on Earth is a great thing. So we've signed an MOU with them, and we've got some internships set up with them. We've also signed an MOU with Padova CISAT in Italy, one of the strongest European-based satellite research groups associated with any university in the whole of Europe. We're in the middle of trying to establish an MOU with the European Space Agency. We've already reached out to them a couple of times. There's been some backwards and forwards, and we hope that, the virus aside, I think we already would be further along in our discussions. And we're also looking at signing an MOU with the Indian Space Agency. And so, we will partner strategically with any group that kind of matches our vision and our intentions and our strategic plans for us. And what can we bring to the table for them? Well, we've got lots of great scientists working at Hong Kong U in the LSR. We've fountain of ideas and things. We have a very good university behind us to back us up. And so it's all about building effective relationships which we can together, you're better than you are apart. So that's the kind of plan, is that together we build something that we couldn't have done on our own so easily. And so, we're very careful about who we're partnering with. And, even Macau, Macau have got this state key lab in China. We're looking at working much more closely with them. So we are open to working. And in fact, with HASSE, which is an American-based company with strong Chinese interest for education, that's hopefully become a partner with us too, as we try to reach out to young minds and get them interested in STEM subjects like, science, technology, engineering, mathematics, because people need to know the scientific method so that all that wool can't be pulled over their eyes with all this nonsense they hear on the TV, so they can make up their minds based on proper evaluation of data.
That's right.
Very important.
Check their facts first.
Check facts.
Excellent. I'm happy to know that. You have mentioned...
You read.
I'm sorry? Don't believe everything you read.
And don't believe everything you read. Yes.
That's true.
Use your brain to be critical. Critical
and
thinking.
Cross-reference
Very
everything.
important.
I absolutely agree. That is something.
Provenance. Yes, provenance. Very good. Very good. Very good, Elena. I love it. Okay. Sorry about that.
It's something that researchers learn and have to do while they study. And I know that Hong Kong University offers programs in space-related education. Am I correct? You guys have a master's degree even. There's either a 1-year or a 2-year program.
Yes, we do have a... Yes, thank you for bringing it up. That's something very, very close to my heart, because it's a brand new taught postgraduate master's, which we're launching in September, all being well. And it's interdisciplinary. So that is to say that if you look at the, there's a series of electives and core courses. It's a 1-year full-time and 2 years part-time. And it's the first program of its kind in this part of the world. There's nothing quite like it has been done before around here. And of course, there are other programs around the world, some very good ones. And in fact, we've gone to them to ask their opinion as we set up our own one. And we're very grateful to the tremendous support that they've shown the University of Hong Kong as we move this program forward. But if I just look at some of the core courses, and there's 36 credit points you need there. One of them is like space flight propulsion. So, a bit of engineering and everything going on there, and mechanics, etc. Then introduction to space weather. So you might need to know a little bit about magnetohydrodynamics and, and solar flares and all that way you need to protect your satellites from space weather. Then remote sensing, how we're using satellites in space to try to look down at the Earth so we can map resources, understand climate change, and all those other things. Then radiation detection and measurement. That's another core course. And then we have space entrepreneurship as a core course, because we know there are a lot of people out there that are interested in space and space technology, but they also want to get into the startup regime. They want to get into companies. They want to try to, become part of this $1.2 trillion space economy that Morgan Stanley thinks will exist by 2040. So there's huge growth potential in the world for the space economy. And, you know, and there's so many satellites are being launched now. A lot of them are small microsatellites or picosatellites, and of course that's a tremendous growth. And then the final one is small satellite design. So that's just the electives that we're doing. You can already see it's quite interdisciplinary in its structure. And this, I think, is one of our unique selling points. And it'll be taught by, you know, experts both at Hong Kong U, and we've got experts coming in from Zhejiang University and Nanjing as well, and guest lecturers from the University of Padua and all these other places. So we have a fantastic set of lecturers and a great series of courses. For example, we've got how many? We've got courses in the electronics and statistics as well, big data, AI, machine learning comes into all of this as well. You know, vast amounts of data coming down from our satellites in space. How do you deal with it? How do you handle it? How do you triage it, filter it, compress it, analyze it, visualize it, all these kind of things. So on my course, actually, that I'm teaching is climate change. No, that's a lie. Habitable planets and the origin of life. That's the one I'm teaching. And so that's an elective, though, so not all students need to do it. And that's also, we're looking at SETI and the Drake equation and habitable zones and panspermia and extremophiles and all these kinds of things in that course. From also using biology and physics and the mathematics in there too, of course. It's a graduate level course, it's masters. So why don't I just quickly, that's the leaflet that we have. Yes. Master of Space Science from the University of Hong Kong. So there is still time to enroll. If there's anybody out there listening in that's thinking of a career change or thinking of doing a master's degree, then there's still time to enroll, by the way. The close off is in about 10 days' time for foreign students from overseas, and people from Hong Kong can enroll up until the end of this month. So anyway,
so
selling. I'll stop selling my program now. It's up to you.
No,
check it online if you like it. Let me know.
Don't stop quite yet. Could you tell us something more about the application criteria, for example? What would be the prerequisites if students were interested in enrolling? What would they already need to know or
have? Very
good
question. Well, because it is interdisciplinary, we're looking basically people do have a strong technical and scientific background. So they should have had some major in physics or mathematics or astrophysics or computing or engineering or geophysics or something like that, something where we can demonstrate they've done enough physics and maths and some of these other things in their undergraduate career or through later experience that gives them enough grounding that they won't find the course impossible to do. You know, the course is designed to be attractive to a broad range of technically and scientifically competent individuals. So it doesn't mean you have to be a great physicist or a great mathematician or a great engineer. You just need to be competent at the level of about second-class honors. Second-class honors or a GPA of 2.8 or above. I mean, these things are hard to compare from university to university, etc. But basically, if you need to be able to speak English well and read English well and listen to English well. So you need to get a score of at least 6 in the IELTS or above. And you need to have come from a decent background, a scientific, technical background that's appropriate along the lines of all those things I just mentioned. So quite a wide variety and quite flexible, and have a decent GPA. But second-class honors, you don't need to have first-class honors or even a 2-1. Decent second-class honors can get you into this program. And so even though it is quite selective, and you know, this is our first year. And as we go on, I think we'll get stronger and stronger, and we'll learn more. But we think we've already got an extremely exciting set of courses for us. Now, apart from the courses and apart from the prereqs, which I've just mentioned, the other thing we've got a lot of is scholarships. So we've got about a dozen scholarships to offer of 50,000 Hong Kong dollars each. And we also got a lot of internship opportunities. So students can do internships of 8 to 12 weeks in the UK at the National Natural History Museum, in Italy at Parabasisas, perhaps at ESA in the future, and also you know, in many places in the mainland at Zhejiang University and Nanjing University, which are the strongest microsatellite and space science groups in the whole of China, and also with some of the companies, including commercial companies like DFH, which are manufacturing satellites. They're looking for bright people to come and work in their factories and their manufacturing sites and their design offices and their engineering groups. And so, we see this program as being a conduit, a pathway into space, into the space economy. The burgeoning space economy that's going to be $1.2 trillion US by 2040, according to Morgan Stanley. I can't predict the future, but I think they know what they're talking about.
Well, I certainly hope so. It sounds like it's a really well-rounded program. Many different courses that are part of different industries even. You've mentioned economics, you've mentioned physics, obviously, you've mentioned other fields. It sounds like it's a really, really well-rounded curricula, and also the students will have an opportunity to do internships with those companies.
The good thing is, apart from the core courses, the electives are quite diverse. So if you're more interested in the engineering side, you can pick more of those courses. If you're more interested in this sort of data analysis and data products and AI side, you can do more of those courses. If you want to do more on entrepreneurship, you can go also pick the one on project management, as well as the one we're doing on entrepreneur. So there's different streams you can sort of tune to, depending on where your interests might lie. And the other thing I should mention is a capstone project, which you have a little research project where one of the staff members, like myself, will look after a number of students and I'll do little research projects, either at Hong Kong U, in the LSR, or maybe in one of our sister labs, one of our partner universities overseas, whatever. Plenty of opportunities as well there.
That sounds great. And when students apply for those programs, they can apply for the scholarships at the same time, or is that like a separate process that they would have to go through? I believe scholarships would be very important. Yeah,
the scholarships are a different process. I mean, you put in your normal application, and then you would then write to a member of the program, like myself as a program director, and say, I'm interested in the scholarship. Well, basically, all I'm looking for is a 2-page, no more than 2-page description of why you think you should get a scholarship. Now, the criteria for these scholarships are mainly two. One is academic excellence and merit, but the other is a combination of academic excellence and merit and financial hardship or disadvantage, because we really are trying to reach out to those students that might not otherwise have a chance to come and do a program like this because they can't afford the fees. And so we want to try to help those students if we can through this scholarship program. So we've dedicated 4 such scholarships purely to those that may be a disadvantage of having a difficulty of putting the fees together. And there's more to come. So, we're getting more and more sponsorship coming in, because I think people are attracted by the excitement that our program is generating. And we're very excited to be able to put it on.
Of course. And this being the first year, I believe that it will just go up and up from here. You will have more applicants every year. You will have more opportunities, more different classes, and different institutions to cooperate with.
We hope so. I would say that if nothing, we like a challenge, because launching this postgraduate program in the middle of a global pandemic, you can imagine, it's not the easiest thing to be doing.
That's true.
Yeah. So it's so we've made it. It's a little tricky for us given the circumstances, but we do have quite a lot of applications already. We're going through them all very carefully and assessing. We're interviewing every potential student as well. So any of you that are interested, you will, if you're good enough according to your background, GPA, English scores, etc., then we will go through a triage process. We will select candidates for interview, and then we will interview you.
Excellent. Well, I hope that some of our attendees will apply.
I hope so too. It'd be great if they did.
I believe that they have been not only motivated, but also inspired by you and your journey as a scientist and what you have discovered. To those of you attending right now, I would just like to remind you that Professor Parker has discovered a comet that has, he has named after himself.
Check it out.
So if your dream is to, achieve something in your life, perhaps discovering a comet or a distant galaxy could be one of the things you can do to leave your mark, and hopefully a degree from HKU can help you with that. So I really, really hope that we have inspired and motivated not just our attendees here today, but anybody who will watch this webinar at any given point in the future to pursue those careers and those degrees, because it sounds like you really love your job and you see significant results after a day's work. And I think we all should be just striving towards being a little bit more like you, Mr. Parker.
Well, Elena, thank you very much for your very kind words. I can't help myself. This is the kind of person I am. I just like trying to connect, trying to help, trying to educate, trying to play a role. Thank you very much. Great questions.
Now, speaking of questions, I would just quickly like to remind our attendees here that you still have time to send your Q&As into the Q&A section. If you see a question that is similar to yours, so something that you would like to ask yourself, please upvote that question instead of writing a new one, because we already have dozens and dozens of questions that you guys would like to ask, but we will not have time for all of them. So if you see a question similar to yours, please upvote the existing one instead of writing a new one. And Professor Parker and I will do our best to answer as many of your questions as we can. Now,
certainly will.
Would you like to add anything else, Professor Parker, about the program, about your work, about you know, how important it is to pursue those degrees and those careers? Because you've mentioned, of course, the pandemic is making everybody's life and work much more difficult, but especially in those times, probably you know, putting emphasis on sciences and you know, on cooperation across different fields, and cooperation across different industries, and you know, countries and borders. I feel like that is a really good time for us to, you know, inspire and motivate the youth, the upcoming generations to, you know, to study those fields, to pursue those degrees, to cooperate internationally, and to, you know, to try to better not only ourselves but also, you know, all of humanity. Is there anything else?
I think what your words are wonderful, wonderful words, Alina, and I endorse them very strongly. I think you know, we're living in an amazing world, an amazing age in terms of technology. When I look at what was around when I was a young boy and the first pocket calculators came out, I think, oh my goodness me, look at this incredible thing. And now pocket calculators is one of the things, one of the apps you have on your mobile phone. You know, and so I think of Star Trek and I look at what's come true. I mean, we don't have warp factor 10, we can't travel faster than the speed of light, but nevertheless, the advances in technology, and you know, we're entering a world of AI and big data and automation and you know, an incredible ability to modify the human genome and genome of many organisms, and to create nanotechnology and to do incredible things with technology. But it also brings lots of dangers, and the people need to understand what the risks are, or else, you know, you end up creating something like through genetically engineered crops that end up killing all the bees, for example. And we know that bee collapse, and there's colony collapse of bees, is a major problem already. And if the bees disappeared, human race would probably disappear fairly shortly afterwards. So everything's interconnected and in a very difficult way to understand sometimes. There's so many overlapping interdependencies in our complex world. And we're seeing that now as we enter something called the Anthropocene. You know, this is the new age of geological age, where the world is changing as a consequence of our actions as a species. You know, we are the dominant species on the planet. Nearly every other living thing is suffering because of us in one way or another, in my humble opinion. And so, but we have an opportunity to do something, and we have an opportunity to change where we're going, you know, and technology, I think, it will be the savior of our race. Technology, if we can master it, if we can go away from fossil fuels and suddenly we get cold fusion working or something, you know, and there's more power now generated through renewables in many countries than you're getting from fossil fuels, and that needs to accelerate. Perhaps this one silver lining of this terrible pandemic is the people talking about greening the economy. You know, I think that's something we should do. But, you know, basically I think that more that students can understand the scientific method and apply critical thinking skills to information and to data, to sift it, to analyze it, to understand it, and therefore make more informed decisions in their daily lives about everything they do, from what they buy, to how they travel, to what they eat, to how they interact with other human beings by distance, or I'll get in my car and drive 10 meters to my friend's house, you know, rather than walk. I think all these things matter. And you say, what can I do as an individual? Well, if every person as an individual, all the billions of us, did something, then everything would be totally different.
Absolutely. Yeah. Absolutely. So what we can do as an individual is educate ourselves and take those little steps that we can on such a small scale.
Exactly, exactly. We can all make a difference. All of us, everyone.
And I surely believe that by speaking to you or other, very inspiring and inspired human beings like yourself, we will actually eventually, motivate enough people to want to change and better themselves and to, educate themselves a little bit more, take those little steps, and then wait for technology to, take us there to the future. So we have something to look forward to, I believe.
There could be somebody listening to us now who has a spark of an idea that can transform the planet for the better.
Absolutely. Let's hope so.
Yeah. Let's hope so. Fingers crossed. Toes crossed. Everything crossed. Yeah.
Excellent. Thank you so much, Professor Parker. Now, I have no more questions I would like to ask you myself, but our viewers definitely have plenty. So if you don't mind, we would like to proceed to a Q&A part of this interview, if that would be okay with you.
I'll do my best to answer them, but I can't promise I will have all the answers, but I will do my very best to answer those that I can.
Excellent. So let's see. Our first question here is from Fernanda, and it's been uploaded quite a few times. She asks about how do you know that 27% of the universe is dark matter if it does not emit electromagnetic radiation to measure? So what other ways of knowing then we have?
Yes, as I was saying in my talk, yes, you're absolutely right. Dark matter doesn't emit photons, and we can't see it emitting across any part of the electromagnetic spectrum. But what we do know, as I said, is that gravity works. We think we understand gravity, and therefore the way that dark matter betrays itself, and the reason why we think it must exist, is purely by the influence that the gravity of this dark matter has on the stuff that we can see and the stuff that we can measure.
I see.
So it's basically, it betrays its presence by the gravitational effects that it has.
Mm-hmm. So basically we know about it thanks to gravity, because we already know the gravity exists. We already have it it's a really well mapped concept. So knowing that, we can do the calculations that dark matter exists. However, we cannot prove it quite surely yet.
Well, we know it must exist. We just don't know what it is. We haven't seen a dark matter particle. We haven't been able to take one and say, look, I'm holding a piece of dark matter in my hand right now. We postulated the kind of things we think it might be made of, but we have no proof, no experimental proof of what dark matter is actually made of.
I see. And if I could follow up with the next question from Francisco Julio, he was wondering, what do you think would happen if the whole universe was actually made out of dark matter? Because we know that it's just a part of it. What if all of it was made of dark matter? Would a universe like this even exist?
Well, we wouldn't be having this conversation. If all the universe was dark matter, nobody would be around to postulate about it. So, I mean, then we start getting into the realms of, parallel worlds and parallel universes, and every universe you could possibly think of must exist somewhere in some parallel sense, and some universes are made up purely of dark matter and nothing else. Other universes are made of just of baryonic matter and nothing else. And, you can postulate and come up with theories for all of these things. But that's all they are, theories. All we can think of at the moment is the only universe that we know definitely exists at the moment, and that's our own. And then all we can do is try to understand it the best way we can. And you have to understand everything about astrophysics depends purely, well, until very recently, depended purely on the number of photons we collect with our telescope. We're collecting photons from all these astrophysical phenomena around the universe, and we're trying to understand what it all means. We either make images with those photons, or we turn them into spectra and look at the spectral signatures of objects because of the photons we receive from them. That was until, in fact, we confirmed the existence of gravitational waves a couple of years ago through the LIGO Laser Gravitational Observatory, Laser Interferometer Gravitational Observatory. The LIGO observatories detected the very first gravitational wave signal from two coalescing black holes of several tens of solar masses, and now we've had dozens of gravitational wave detections, and now we have a whole new branch of astronomy. Einstein was right. And there are gravitational waves, and so now we've got this other branch of astronomy is created within your lifetimes using gravity. So yes.
So since we've come such a long way in such a short time, and now at the moment we do not really know what dark matter is made of, one of our next viewers, Vicente, was asking whether you think that it could be dangerous to perhaps study dark matter further. Is there perhaps some kind of a power that we are not aware of quite yet, that dark matter could possess, and that could turn out to be potentially dangerous to us as humankind?
That's an interesting question. There's so many things that are dangerous to us. I'm from Australia, and some of the most dangerous creatures on our planet, live in my country. So crocodiles and spiders and sharks and snakes and anyway. So danger is a relative term. Yes, something dangerous that could wipe out the entire planet. Well, yes. I mean, we could get hit by a dark matter bomb that could pass through the Earth, warp it into something horrible. But the more likely problem is going to be from a nearby exploding star showers the Earth with gamma rays and destroys all life, or we get hit by a massive asteroid that wipes out all life. These are the kind of clear and present dangers, if you will, which is why NASA has this program looking for all the near-Earth asteroids it can, so that we can assess the risk of any one of them. The thing that wiped out the dinosaurs 65 million years ago was only a few miles across. If something hits us that's 100 kilometers in diameter, that's going to extinction level event right there. So in terms of dark matter though, we don't even know what kind of how it's spread. We kind of know where it is. We kind of know overall what the energy density per cubic centimeter must be, but we don't know if it's concentrated in small primordial black holes or is spread thinly. So we don't really know the answer to those questions. So and also the physics of it we don't really understand. And so, I think maybe this question is alluding to the idea that in the Large Hadron Collider, you might create some dark matter, strange particles, which then suck everything in and destroys the Earth. Well, who knows? But it's highly, highly unlikely.
I remember when I was younger, when they were opening the CERN Collider, there was talk about that we don't know what kind of experiments the scientists will be running there, and who knows that if perhaps they would be able to even create a small black hole that would then eventually, swallow the entire Earth. Yeah. I just remember that very distinctly from when I was a child and when they were opening it, and I was even afraid of it, thinking, why would they do this? Why would they put all of our lives in such danger, and what for? But I feel like black holes are such a big topic. People talk about them a lot these days, especially considering the recent animation or the photo of a black hole. And that is one of the questions that another one of our viewers asked. Francisco Julio is wondering whether you think it's true that, black holes could change the way or everything we know about the physics, because physics of black holes and physics as we know them on Earth are quite different. So what if we study black holes in further detail? Do you think that would change the physical rules that we perhaps learn at school as students?
Black hole physics is extremely difficult and very complicated. Stephen Hawking dedicated decades of his life to trying to understand black holes. He came up with the concept of Hawking radiation, so that black holes eventually, over eons, would evaporate away, depending on how much mass they have. They eventually wink out of existence. And so, black holes, we were postulating that you could maybe use them as wormholes to transform yourself from one part of the universe to another instantaneously, to traverse great distances. But then how do you deal with the tremendous gravitational forces as you go into the black hole? Spaghettification has been talked about. So look, much cleverer people than me, theoretical astrophysicists, have been studying black hole physics for a very long time, and understanding has emerged of how we think black hole physics works. But when you're talking about a singularity, when you're talking about something the size of a pea having the mass of the Earth, it starts to warp the mind. You can't really comprehend that kind of thing. Even trying to comprehend the scale of the universe and how big it is, and etc. It's mind-blowing. And mathematics is a language that enables us to describe these things. And sometimes we can use a language to describe something which we can't conceptualize in our own brains. So that's the issue. So physics has evolved. It's changed a lot over 100 years. And who knows what the next 100 years will bring in our understanding of physics. So far, Einstein's revolutions of physics have proven to be correct. And every time we test his theory, more and more accuracy, they're still holding true. But every theory is just an approximation to the truth. You know, it's like photons. What's a photon? Well, sometimes it's a particle and sometimes it's a wave. So wave-particle duality, how the hell does that work? You know, a lot of these things are difficult concepts to grasp. And so we're looking through a murky glass darkly, you know, and trying to understand clearly what's on the other side is not always easy. And we don't have all the answers, that's for sure.
That's right. And speaking of answers, another one of our viewers, Augustine, he is quite interested in quantum physics, and he even says that he would like to study mathematics of quantum physics and equations. And his question to you is, well, he would like to know, where do you think would be a good place to start? What kind of advice would you give him, apart from good luck, obviously, which I believe he will need? Where could he begin?
First of all, you need to have a very high level of mathematics. You need to understand fundamental mathematics and calculus and differential calculus and particle physics and quantum physics. And you need to get a good understanding of these. To do this, there are some tremendously good textbooks out there that you can read up on. So look for the ones that have the best reviews and the ones that are used at the top universities as graduate text or undergraduate text. And also, if you want to do it at a university, then you should go to the very best universities in the world with the strongest reputations for quantum physics. So you're looking at in the UK and Europe, the best would be you know, Oxford and Cambridge and places like that, and ETH Zurich. In the States, you have the Ivy League and you have MIT and Caltech, and so, you know, the best universities in the world happen to be in the English-speaking world, actually. So America and the UK dominate the top 20 places across the world at the moment. Universities in China are now jumping up the world rankings very quickly. You know, in Europe, you have very strong universities like ETH Zurich, one of the top 10 universities in the world. And so you just have to be very careful of where, you know, pick the best you can possibly get into. Always aim for the highest possible level you can and try to get there. If you can't get there, you go down just one rung and try there. But as long as you're realistic, there's no point trying to go into these places if you've only got a second-class degree. You've got a second-class degree, get another one and it's first class. Then, you know, so you've got to count your dreams in the pragmatic appreciation of who you are and what you've achieved and what you think you could achieve. So I'm not saying don't be a dreamer, don't try your best, always try your best, but you've got to be crouched in, you know, there's nothing worse than having dreams shattered because they're unrealistic. You know, as a scientist, you know, I look at the evidence and I look at myself and say, well, I think I'm here. This guy, I hate him because he's right up here. But, you know, so, you know, you've got to evaluate yourself and try to be honest to yourself and what you can achieve. And if you believe in yourself and you have the ability, there's nothing you can't do. So the thing is to have, you know, but aim for where you think you can get, but don't sell yourself short either. Never sell yourself short either. And you don't know how far you can go until you try. If you don't try, you won't go anywhere.
That's true. I believe so, and this is something that we here at HASSE also do. You know, we try to encourage our students to aim higher and dream big, but also still have realistic expectations, and, you know, not, as you mentioned correctly, have their dreams and hopes shattered just because perhaps they expected something else. So I believe that's something that we can relate to as well. As educators, we try to push our students towards doing exactly that. And speaking of students, I actually have a question here from one of my alumni, Martin, who's asking about, again, going back to dark matter. And he would like to know whether ordinary particles could decay into dark matter. Could they perhaps switch form? Because you've mentioned that we don't really know exactly what dark matter is quite yet, but we already know what our ordinary particles are. Is there any way they could be working together, or, you know, one turning into the other?
I'm not a particle physicist, but I do know, you know, things like we think that neutrinos can change flavors. The ones that are emanating from the sun switch from one kind of neutrino to another, and that's a fundamental particle. You know, a neutrino is another whole ball game. Again, you know, billions passing through the Earth without interacting with any matter at all. And we believe dark matter is similar. It doesn't interact at all. You know, we think that the idea of a sterile neutrino could be sort of a hint at a dark matter origin. But, you know, at the end of the day, if you're doing these controlled experiments with particle accelerators, where you have an energy and mass budget that you think you can understand and control, and then you look at the showers of fundamental particles that are created and decayed and everything else, and you can understand those, then if at the end of the day you add everything up and there's something missing, where is it gone? So, you know, you need to design an experiment where you can actually say, well, particle X of weight Y suddenly became particle X plus of weight Y minus. Mm-hmm. And the difference is energy, but there's no photons. So where's it gone? It become a dark matter particle, for example. So you need to have controlled experiments where you think you understand the entire mass and energy budget. If you don't have that control, I'm not sure you always will be able to have that control that you need at the precision level you need currently with our technology to be able to do an experiment like that. I don't know. But, you know, postulation is fine. You know, design an experiment. You know, the thing about theory, anybody can come up with theory, any ludicrous theory you like, but unless it's based on some kind of testable, you know, approach, I mean, that's how theories get tested and proven, is that they predict, your theory predicts an experiment that you can undertake and get a result that matches your theory. That's the scientific method.
Right. And is there any way in which dark matter could interact with Earth, for example? Would that be a way to, you know, test the theory of its existence? If its existence, sorry. Could it interact with Earth?
We have no evidence that dark matter is interacting with the Earth. There's no evidence that I can think of or I've read that I can say about that. I mean, these are interesting questions, but they're not questions that I have the expertise to be able to answer, and I'm not sure anybody does. But the problem with dark matter is that it doesn't. If it was something we could measure easily, we already will have done it. If it was something that was within the realms of our physics that we could explain it simply, we'd have done it. We've come up with all sorts. We know it's there. We know it has mass. It could be lots of primordial black holes. It could be some fundamental particle with mass we haven't discovered yet. It could be lots of free-floating brown dwarfs. You know, there's all kinds of ideas what dark matter could be, but we haven't been able to prove any of these ideas. None, not a single one.
I see.
So the jury is out. You know, science is trying to understand it. Experiments trying to understand it. But, you know, dark matter is out. We see dark matter's effect on large scales in the universe. We can't go out there and do an experiment in a cluster of galaxies. All we can do is measure photons coming to us and gravity waves. That's it. Mm-hmm. Until we, you know, have a spacecraft that can go out there and do things in deeper space, we can only measure things that come down to us on Earth. And that's just photons, particles of dust that come from outer space that fall down and rain on the Earth every day, you know, and gravity waves that occasionally pass through the Earth and create very slight contraction of matter that we can measure, actually. You know, gravity waves, we're measuring 10 to the minus 21 of a meter in strain to be able to detect a gravity wave. I mean, that's just astonishing. I didn't think we'd do it in my lifetime, but we've already done it. I didn't think the technology could do it, but it has. Years above schedule. So, but there's incredible tight, you know, think of a 10 to minus 21 of a meter that's smaller than the diameter of an atom. You know, it's ridiculous. Anyway.
Excellent. I have another follow-up question from Max. Hi, Max, by the way. Thank you for tuning in, one of my past students. And he would like to know whether you think that dark matter could, at high energies, be decomposed in subparticles that cancel their charge, as quarks in neutrinos do. So do you think that dark matter...
I'm not a particle physicist. Yeah, these are great questions, you know, but you need to speak to a particle physicist. Mm-hmm. I'm sorry. Yes, they possibly could, but you know, I'm not speaking from a theoretical understanding of particle physics. You know, if I was a particle physicist, I could probably answer you that question in terms of, you know, all the kind of particles that you've been mentioning. I remember at school physics, I learned a little bit about gluons and quarks and all these kind of things, and hadrons and electrons and muons and all these things, but that's not my area, I'm afraid. Mm-hmm. I know something about dark matter. I know about its astronomical effects, that we can measure as an observational astrophysicist, and I understand them, and it's all to do principally with gravity. I know about some of the ideas of what dark matter could be, but the actual nitty-gritty of the physics of dark matter and the particles it may or may not consist of is way beyond my expertise level. I'm sorry.
Understand.
I mean, I need a career in it. I need to spend 30 years just working on that to be able to answer you.
Understand. Now, Lorenzo was wondering, oh no, please don't apologize. Everybody has an area of expertise, and I feel like in physics it's such a complex field. You have to choose your focus really, really carefully, and one person cannot possibly know everything about everything. That's just out of this world.
I tell this to my PhD students. I tell them at the end of their PhD, you will know more about what you're doing than I will ever know, because they're spending 4 years of their life honing in on one subject, in an area of late stage cellular evolution. So I tell them, I'm across lots of different things, and I've done lots, but I'm not going to get. You spent 4 years doing that. I haven't spent 4 years doing that. I did for my own PhD, but not for yours. And I've guided you, and I've mentored you, and I've directed you, and I've helped you, but I haven't gone in to the literature and like you have, because I don't have time. I'd be doing a PhD myself again if I did that.
Imagine having to do one every 4 years on a different topic. No, not doing it. Sorry, not doing it. One is enough for me. 411 pages. Thank you very much. 211. 411. 411. That's quite a hefty book.
It was this big. It was 3 inches thick.
What was the topic of your thesis or your dissertation?
Oh, it's a galaxy redshift survey, observational cosmology. So in my early career, I did galaxy redshift surveys, but then in 1998, I moved into narrowband wide field surveys of the galaxy, and then I discovered large numbers of planetary nebulae, and I thought, I think this is my new field of research. I like discovering things, so when I found lots of planetary nebulae, I sort of moved over, segued from galaxy redshift surveys to planetary nebulae, more local.
Did you name those after yourself as well?
I'm not that. I don't have that much of an ego for that. So I know a lot of amateurs name all these planetary nebulae after themselves, but I haven't named a single one after me. All I've done is I've called them after me and my team. So if I'm like me, PHR would be like Parker, Hartley, Ricet. BMP would be like Birkby, Mazalski, Parker. PPA is Parker, Peo, Acker. So all the people I'm working with, I keep my P in there for Parker, but it's just like in like hidden as PPA, MPA, PHR, but never Quentin or Parker. No, never done that. The only thing I've named is a comet. Then I shared it with my friend. So I'm not driven by fantasies of glory with having everything named after me.
They say sharing is caring, and if you share your achievements with somebody else, I feel like they become even more significant. Because you can share your satisfaction, perhaps, and sense of fulfillment with other people.
That's it. Very good. Yeah, giving people credit, showing that you're a team player.
That's right.
Helping them out.
Where credit is due.
Absolutely.
Great. I think perhaps we have time for one more question. And
okay.
Let's see. Okay, last one about dark matter, I promise, because it's the last question overall. But Richard is wondering whether there is any pattern in the distribution of dark matter. So I believe that you use your telescope to study different parts of the universe, but also dark matter could be, I guess, an after product or a byproduct of your studies. Is there any pattern?
Yeah, I mean, dark matter. What I recommend your question
more about that.
Sorry, what I recommend your student or the person asking the question does.
But
sorry, can you repeat that? Sorry, it's gone. Can you hear me?
Yes. Let me go back. Yes, I can hear you. Can you hear me?
Yes, mapping the dark matter. Yes. What I suggest your student does is he looks up on the internet the bullet cluster. And if he does that, you can actually get one of the best maps we currently have visualized of what we think the dark matter distribution on the larger scales, that is on the scales of clusters of galaxies, looks like. We haven't got small scale maps of dark matter, but we have large scale maps of dark matter. So we can see, the dark matter's here and it's distributed a bit like this. And of course, this theory that goes behind that about how we think it might be distributed. So we've got to the stage where we can kind of map where dark matter is based on, again, it's the effect that its gravity has, either through gravitational lensing, in this case. In fact, it's through the gravitational lensing in the bullet cluster. So the image shows you X-rays from the hot X-ray cluster gas, which is one way of finding rich clusters of galaxies, actually, by looking for X-rays. But also by the effect that the gravity of the dark matter is having on material behind, and how it's warping those images. And so that's very interesting. So I recommend the student has a look at that, and it'll give you some idea of how we're currently being able to map dark matter.
Excellent. Thank you so much, Professor Parker. I think this will be all from us here today. There are still many more questions our students wanted to obviously ask you, but unfortunately we do not have that much time. However, I would like to highly encourage all of the students and all of the attendees that have any questions to continue self-educate themselves and go and research those topics, and do not stop. Keep a curious mind and an inquisitive mind, and don't stop asking important questions. Go pursue those degrees and go pursue those careers, because as you can see, one day perhaps you could be naming galaxies and nebulae and comets after yourself if you get those degrees. And I also hope that perhaps studying at the Hong Kong University could help more of you, learn answers to these questions by yourself. So you don't have to go and ask the experts. You will just become the experts in those fields one day. And so I would like to thank you very much, Professor Parker, for your time, of course, for answering all those questions patiently, for being just such a great motivation and inspiration to all these young men and women. And hopefully, we here today, and especially you, actually did inspire them and motivate them to pursue those degrees and those careers, because it seems like you're such a happy person. You seem to love what you do. And we're all really curious about, what other achievements you will, achieve, what other goals you will reach, and, better not just science, but also, all of humanity in a way or another. So thank you again for your time. It's been a great pleasure to have you with us here today, and I hope to see you soon sometime.
Thank you very much, Elena. You've been a wonderful host, and it's been great to be able to talk to so many students, and I hope they've enjoyed the discussion and the presentation, and I've tried to do the best I can. As I said, I'm not a world expert in dark matter, but I do know hopefully enough to keep your interest there. Good luck with whatever you're doing. It's great that you're interested in this webinar and interested in the HASSE and what they're doing through their fantastic webinar series. I strongly recommend it. I've really enjoyed participating in it, and thanks to James for bringing me on board and giving me the opportunity to talk to you all, not just about dark matter and our first satellite that we're launching in July, but also about our wonderful program in space science, which perhaps some of you may even enroll in. I hope so. Anyway, take care, everybody. Have a great night or great day or wherever you are, and don't forget to always try to keep going forward. Thank you very much.
Thank you so much. And good